provided by Thomas Allgaier and Frennis, based on the most relevant LinkedIn posts about electrification and battery technology in calendar weeks 28 and 29. Frennis is a B2B market research company that supports automotive suppliers with building feature-by-feature competitive intelligence that shows exactly how their product stacks up against the competition. You can find more info in the description.
All right, look at it.
Yeah, so imagine you're buying $1 million fleet of electric trucks for your logistics company. I mean, the vehicles are shiny, the drivers are trained, your routing software is, completely primed.
Sounds great so far.
Right. But then you discover that the local power company, legally, will not let you plug them into the grid for another 24 months.
Oh, wow. Yeah, that's a nightmare.
It's a specific nightmare that is quietly choking the entire EV transition right now. We're looking at a stack of industry insights today that completely shatters the illusion that electrification is just about, building enough cars and bolting enough chargers to the pavement. The narrative has fundamentally shifted. The vehicles are here. So the question now is, what breaks next as this massive adoption scales up?
Right, and the physical constraint emerging in the background here is the grid itself. We are seeing these incredible exponential gains in global EV sales and battery manufacturing.
Which is great news, obviously.
It is. But as with any exponential technology curve, when it hits the physical world, the bottleneck moves. It is moved from the assembly line directly to the copper wires buried under our streets.
The copper wires, yeah.
The binding constraint for the next decade of mobility isn't automotive engineering. It's civil engineering and localized power distribution.
I mean, we have all these companies advertising these lightning-fast 400-kilowatt charging experiences, yet the infrastructure beneath it seems to be just groaning under the weight.
Totally groaning.
Sarah Ellis and Rachel Lai both pointed this out in their recent posts. They're tracking charging projects across Europe, and the primary source of delay isn't a lack of physical charging hardware rolling out of factories.
No, it's not the hardware at all.
The bottleneck is the grid connection limit.
Yeah, it is the agonizingly long wait time to actually get the necessary electricity capacity routed to a specific site.
Yeah.
We are talking about grid operators needing to lay new high-voltage cables, upgrade substations, and, install these massive transformers.
And those take forever, right?
Exactly. Those transformers alone can have a lead time of 12 to 24 months. And that's assuming you can even navigate the local permitting process easily.
Wow.
So you have operators with pallets of ultra-fast chargers ready to deploy. But the local utility simply cannot deliver the megawatts required to turn them on.
It's basically like buying a state-of-the-art high-speed fiber optic router for your house, but the city only provides you with a decades-old dial-up internet cable.
That is a perfect analogy.
You can have the most advanced piece of routing technology sitting in your living room, but if the pipe feeding it from the street is tiny, you are going to be buffering. The bottleneck is the connection, not the tech.
The pipe metaphor is highly accurate. And the volume of data, or in this case, electricity trying to push through those pipes, is about to scale exponentially.
Right.
Christophe Lefilibert shared some data from PwC Strategy's 2026 Outlook that contextualizes this perfectly. They project that EV charging demand in Europe will hit around 200 terawatt hours by 2035.
Okay, let's scale that number for a second, because 200 terawatt hours is completely abstract.
Very abstract, yeah.
That is roughly equivalent to the entire annual electricity consumption of a country like Spain.
It's wild to think about.
We're essentially talking about plugging a medium-sized industrialized nation into the existing European grid, purely to move vehicles around.
Which means the fundamental business model for charge point operators, the CPOs running these networks, it has to shift. It's no longer just a land grab of merely installing hardware in good locations.
Right, it's getting more complicated.
Much more. The core competency is shifting toward software and intelligent orchestration. They have to decide algorithmically where every available kilowatt goes across a network to avoid triggering massive peak demand charges from the utility companies. Or worse, browning out a local neighborhood.
But if the overarching goal is intelligent orchestration to save the grid, how does that actually play out for the person sitting in the driver's seat?
That is the million-dollar question.
Because if I pull up to a charger advertising high speeds, I don't really care about the operator's load balancing algorithms. I just want the electrons in my car so I can leave,
Right, and that is the exact friction point. The macro need for orchestration directly collides with the micro experience of the driver. If the site fails to deliver during peak demand, the driver suffers. regardless of how smart the back-end software is.
Yeah.
Felix Hamer posted a live review from an Ionity charging site in Girona, Spain, right at the peak of summer travel demand.
Oh, I saw this one.
Yeah, he was facing a 20-minute queue just to get a plug, overflowing garbage bins in 34-degree heat and zero shade.
The wait times are one thing, but the power output, he noted, was the real red flag there.
Exactly. The physical units at that station were promising 400 kilowatts of power, but they were maxing out at just 100 kilowatts.
A quarter of the promised speed.
Yeah. The local grid simply couldn't handle the aggregate pull of all those vehicles charging simultaneously. So the site controller aggressively throttled the sessions to prevent a collapse.
So the hardware was functioning perfectly, technically.
Technically, yes. The machine says 400, the grid says 100, and the driver is the one stuck waiting in the heat for 4 times longer than expected.
So, okay, if transformers take 2 years to install, and public fast chargers are throttling customers to protect the grid, something has to give. I mean, you can't just hit pause on the transition to electric mobility while utility companies dig up the streets.
No, you definitely can't.
How are engineers cheating the grid here? Like, how do you bypass a constraint that is so physical?
You basically change the mathematical shape of how you draw the power.
Okay, what does that mean?
Well, if you can't pull a massive spike of energy all at once, you pull a tiny amount of energy continuously.
Oh, right. Mohammed Taha highlighted this exact mechanism. He was observing a new wave of battery-integrated DC chargers from companies like Huawei, Sungrow, and BYD.
Yes, those are super interesting.
Yeah, instead of demanding a 350 kilowatt surge from the grid the moment a car plugs in, these units have a massive stationary lithium-ion battery built directly into the cabinet itself.
Right. They utilize a concept called peak shaving. So the chargers connect to the grid with a very small standard connection, maybe pulling just 40 or 50 kilowatts.
Like a normal commercial connection.
Exactly. And it trickle charges its own internal battery all day and all night.
Yeah.
To the utility company, it just looks like a modest, highly predictable, steady draw of power.
But when an EV pulls up, the charger doesn't ask the grid for more power. It just dumps the energy stored in its internal battery into the car at ultra-fast speeds. The grid is completely insulated from the spike. The car gets its 350 kilowatt charge, and you bypass the need for a $1 million grid upgrade.
It's a really elegant workaround.
It really is. And by the way, if you want to keep catching these kinds of deep structural shifts in the industry before they become mainstream news, you should definitely take a second to subscribe to this deep dive so you don't miss future editions.
Yeah, you won't want to miss what's coming. But getting back to that trickle charge concept, it really solves the problem for public corridors.
Right.
But commercial fleets are tackling this constraint from a completely different angle. They're looking at their operational schedules and realizing they might not need fast charging at all.
Oh, really?
Yeah. Sebastian Hensler shared an analysis of a brewery depot in Freistadt. They run a fleet of heavy electric trucks. And instead of buying those massive 300 kilowatt fast chargers, which again require those 2-year transformer upgrades, they charge the trucks overnight at a mere 40 kilowatts per vehicle for 12 hours.
Ah, so just matching the physics of the charge to the reality of the downtime. Just a slow, steady sip of electricity.
Exactly.
And I imagine the economics of that are vastly superior.
Oh, the economics are totally transformed. You avoid the massive capital expenditure of high-voltage equipment, you avoid the utilities' peak demand tariffs, and, crucially, you significantly extend the lifespan of the vehicle's battery.
Because slow charging generates far less heat, right?
Less heat and less degradation, yeah. If you know exactly when your trucks are sitting idle, you do not need to over-engineer your facility.
Okay, that makes total sense for a regional brewery that parks its fleet every night. But what about long-haul logistics? What about operators where uptime is the only metric that matters and, a truck sitting idle for 12 hours just destroys their margin?
That's a much harder problem.
Right. If they're actively avoiding megawatt grid connections because of the infrastructure bottlenecks we just talked about, how are they keeping trucks on the road? Are they doing battery swapping?
Yes, exactly. They are decoupling the battery from the vehicle entirely. Marcus Enichern and Todor Todorov brought up a joint venture called Swaptopus.
Swaptopus, great name.
It's a partnership between the battery giant CATL and Octopus Energy. They are building a network of over 30 battery swapping hubs for electric trucks across Europe by 2035.
So instead of plugging the truck in and waiting, you drive into a bay, a robotic system drops your depleted 500 kilowatt hour battery inserts a fully charged one, and you drive away in like 5 minutes.
Yep, 5 minutes. And structurally, it alters the entire financial model of trucking.
How so?
Well, it shifts the battery cost from a capital expenditure where you're buying the hugely expensive battery up front with the truck chassis to an operating expenditure.
Oh, interesting.
You essentially lease the energy and the degradation as you go. The fleet owner doesn't worry about battery lifespan anymore because they don't own the battery.
Swapping always sounds incredibly complex mechanically, though. I mean, do we actually have evidence that this works at a commercial scale, or is this just a pilot program generating press releases?
No, it is operating at scale today. Kajsa Ivanson Sognefer reported that NIO just passed 300,000 battery swaps across Europe for their passenger cars.
300,000?
Yeah. Each swap takes about 3 minutes. They calculate they've given millions of minutes of dwell time back to drivers compared to traditional fast charging.
That's massive. And while the hardware engineers are building robotic swap stations to save time, the software engineers are, finding efficiencies on the back end.
Right.
Casper H. Rasmussen shared a fascinating look at how his team is optimizing the maintenance of these massive networks. They used a small, purpose-trained AI model to diagnose EV charge fault data.
I love this example. This is the perfect example of moving away from brute force solutions. Instead of routing all their diagnostic data through massive, expensive frontier AI models like a GPT-4, they trained a tiny specialized model to do just one job.
Which was just reading the telemetry data from a failed charging session and explaining what physical component broke, right? The efficiency gains there are wild. Rasmussen noted this small model outperformed the frontier model 68% of the time, ran twice as fast, and was 150 times cheaper to operate.
150 times cheaper.
Yeah. They analyzed 1.5 million charging sessions for about $1,000. Running that same volume through a general-purpose frontier model would have cost up to $600,000.
That's an insane cost difference.
It proves that as this industry scales, you don't need the biggest hammer. You need the most precise tool.
Definitely. And, if the industry is successfully finding ways to detach batteries from trucks to keep them moving and using highly targeted software to manage the networks, the logical next step is to look at the biggest underutilized asset in the entire ecosystem.
Which is?
The massive amount of energy sitting in passenger cars parked in driveways and office lots.
Right. Because we have historically treated the EV purely as a consumer of electricity, a one-way street. The power plant generates it, the grid transmits it, the car absorbs it.
But an EV is fundamentally just a massive lithium-ion battery on wheels. Thomas Becker and Dr. Jens Berger detailed the BMW Group's Gen 6 eDrive technology and their commercial rollout of vehicle-to-grid, or V2G, in partnership with E.ON in Germany.
Okay, V2G.
The concept transforms millions of isolated car batteries into a distributed, flexible storage network for the national grid.
Walk me through the mechanics of that. Like, how does my parked car actually help the grid?
Sure. So an EV equipped for V2G draws power when energy is abundant and cheap, say during the middle of the day when solar panels are overproducing, it stores that cheap energy.
Right.
Then when demand spikes in the early evening and the grid is strained, the car feeds that stored energy back into the house or back into the grid, selling it at a premium.
Ah, I see.
It flattens the demand curve and turns the vehicle from a passive consumer into an active contributor to a stable energy system.
Okay, I am going to push back here because anyone who has attended a mobility conference in the last decade has heard the V2G pitch.
Oh, absolutely.
It is the ultimate utopian concept. Why should an automotive supplier or a fleet operator believe this is moving from a PowerPoint presentation into physical reality right now?
Well, you answered your own question earlier with the regulatory updates.
Oh, right. The standards are finally catching up.
Yes, because without a universal language for these devices to speak to each other, V2G was impossible. Jaap Berger and Christian Ponseurs de Brouwer pointed to a critical breakthrough, which is the publication of the ISO 1411820 amendment.
This is the protocol that formally standardizes AC bidirectional charging.
Precisely. It's basically a digital handshake. Before any electricity flows backward, the car and the grid have to negotiate.
They have to talk to each other.
Right. The car has to securely transmit its current state of charge, the driver's required departure time, and the price threshold at which the driver is willing to sell power. ISO 1411820 provides the universal protocol for that negotiation, regardless of whether you are driving a BMW, a Ford, or a Hyundai, and regardless of who built the charger.
And this standard is dropping right ahead of the EU's 2027 mandate, which requires new charging infrastructure to technically support bidirectional functions.
Exactly.
Regulators are officially recognizing that since cars sit parked 95% of the time, they are legally and technically demand flexibility assets. The market signals are finally aligning with the engineering.
They are. And this is but that digital handshake introduces a vulnerability that the industry is just waking up to.
Uh-oh.
Yeah, when millions of cars start negotiating with the grid and pushing energy back and forth, the charging port on the front of the vehicle ceases to be just a physical plug. It becomes the critical network entry point into the national power grid.
Marcel Rixen shared a post about a disclosed vulnerability known as CVE 2026-9039 that highlights exactly how fragile this new entry point is.
Right. Researchers discovered that certain commercial chargers were shipping with default root credentials on the vehicle-facing interface. The username was literally root, and the password was root.
I mean, why does a charging cable even have a login prompt? That's crazy.
Well, manufacturers often leave these backdoor access points open, so maintenance technicians can easily run diagnostics or reboot a charger if the software hangs.
Okay, I guess that makes sense.
But leaving those credentials active on the physical pins that connect to the car is a massive oversight. The researchers used an EV simulator board, which is basically a device that mimics a car's communication protocols, plugged it into the charger, and bypassed the security entirely.
That completely flips the cybersecurity model on its head. You aren't hacking a firewall in a server farm. You are hacking a piece of plastic sitting in a grocery store parking lot.
Exactly.
If a bad actor can spoof that maintenance handshake across thousands of V2G-enabled chargers simultaneously, they could command all those vehicles to dump their energy or stop charging all at once.
It's terrifying.
It creates a distributed physical cybersecurity risk capable of triggering localized grid failures. We have to stop treating the plug as a dumb conduit for electricity and start treating it as a vital network boundary.
Very well said. And as vehicles become grid nodes and as charging networks become critical national infrastructure, the batteries themselves are under intense scrutiny.
Yeah.
Whether we're talking about V2G networks, megawatt truck chargers, or passenger cars, every single one of these batteries has to be manufactured, tracked, and regulated.
Which brings us to the geography of the supply chain, and it is shifting in ways that completely defy common expectations. Daniel Chojnowski shares a statistic that catches almost everyone off guard.
I was surprised by this one.
Yeah. If you ask where Europe's EV batteries are manufactured, the assumption is usually Germany or maybe Scandinavia, but it's Poland.
Poland is currently the world's second largest producer of lithium-ion batteries.
And it is anchored by a staggering amount of concentrated manufacturing. The LG Energy Solution Gigafactory in Roka covers 100 hectares, employs nearly 10,000 people, and outputs 86 gigawatt hours annually.
86 gigawatt hours.
To put that into perspective, that is enough capacity to power over 1 million long-range EVs every single year. That one facility supplies roughly 60% of Europe's entire EV battery demand, and it alone contributes around 3% of Poland's national GDP. The sheer industrial scale required to feed this transition is breathtaking.
It is massive physical production. But the looming hurdle for all this manufacturing isn't just securing lithium or scaling factory lines. It's the incoming wave of compliance.
Oh, the bureaucracy.
Exactly. Rosana Balina and Nemanja Mikic brought up the impending reality of battery passports.
Right. Starting in February 2027, the EU is mandating that every industrial and EV battery have a digital identity, accessed via a QR code.
And this passport requires tracking approximately 80 different data points per battery. It covers the entire life cycle from the carbon intensity of the smelting process to the exact origin of the cobalt to the percentage of recycled nickel and even mandatory child labor compliance audits down the supply chain.
I mean, how does an emerging European battery startup actually execute that? Hiring software engineers to build APIs that connect to auditing software in a mining operation on another continent is a massive barrier to entry.
It's huge.
Does slapping 80 data points of compliance burden onto a battery actually help Europe build a competitive industry? Or does it just front-load massive fixed costs for new entrants before they can even reach commercial volume?
That is the structural debate right now.
Yeah.
Because while Europe is focused on regulation, China is focused on execution.
Right.
Merlin Frank shared data showing that China currently drives roughly 60% of global EV battery demand, whereas Europe is sitting at about 20%.
Wow.
China achieved massive economies of scale first and then began regulating. Furthermore, China's own digital tracking system for batteries already went live in April 2026, almost a full year ahead of the European mandate.
So if China dominates the raw volume and beat Europe to market on the tracking software, how does a European supplier compete? Are they regulating themselves out of the race?
Well, Europe cannot compete with China on pure economies of scale or cheap raw material extraction right now. But Europe might compete differently by owning the back end of the life cycle.
Okay, the back end.
Yeah. Julian Renpenning highlighted a startup called Voltfang that provides a perfect example of this strategic pivot.
Right, they're building an entire business model out of second life EV batteries.
Exactly. A lithium-ion battery degrades over time. When it drops to about 70 or 80% of its original capacity, it's no longer useful for accelerating a 2-ton vehicle. But it is perfectly fine for stationary storage.
Sure.
Voltfang pulls these degraded batteries, runs advanced diagnostics to test their internal health, and repurposes them into commercial storage infrastructure.
They are taking something the automotive industry considers waste and turning it into grid infrastructure. It's brilliant because it completely bypasses the raw material bottleneck.
Exactly. No new mining required.
You don't need to mine new lithium if you can just intercept the degraded batteries coming out of cars. Voltfang started in a basement and is now a €250 million infrastructure business backed by institutional capital. If Europe can't outmine or outmanufacture the competition, building an ecosystem where the battery lives 3 different lives before it ever hits a recycling shredder, that could be a massive domestic advantage.
The overarching reality connecting all these sources is that the era of simply manufacturing electric vehicles is over. We are now in the era of integrating them. Every vehicle rolling off an assembly line is no longer just a mode of transport. It is becoming a highly complex node in a shifting, fragile energy network.
And as those vehicles transform into active grid nodes, and as bidirectional charging scales up to balance our energy needs, the power dynamics of the industry are going to invert.
How so?
Well, the ultimate broker of energy in the future might not be the traditional utility companies generating the power. It might just be the software companies that manage, aggregate, and orchestrate the electricity flowing across millions of driveways and parking lots.
That's a profound shift.
Right. The companies writing the code will control the grid. It's a lot to think about.
If you enjoyed this episode, new episodes drop every 2 weeks. Also, check out our other editions on commercial fleet insights, future mobility and market evolution, and next-gen vehicle intelligence.
Thank you so much for joining us on this deep dive. Don't forget to subscribe, keep questioning the infrastructure around you, and we will catch you in the next one.